I want to take a look now at a third order recurrence relation, and we won't do any fourth order recurrence relations. Third order is plenty hard enough for us here in this course, which means that I've got 3 values that I need to know in order to find my next value, which means I have to be supplied with 3 initial conditions. Now, the good news is the steps are the same. The good or bad news, depending on who you are and how much you remember about, say, Algebra 2 and matrices and things like that, is solving that system of equations may be more difficult, or it might be really easy for you if you remember how to do it. So hopefully the little brief review that I'm going to do of those things as we solve this will help you to refresh your memory, because I know that you've learned this before. So again, step 1, just like before, get everything to one side and set it equal to 0. Then write your characteristic polynomial, which is now going to be a cubic function instead of a quadratic. Do we remember how to factor? Well, hopefully you remember the whole p over q thing, where I'm looking at factors of p. So factors of 12 are 1 or 2 or 3 or 4 or 6 or 12, and factors of 1 are just 1. And so I'm taking plus or minus 1 divided by 1, plus or minus 2 divided by 1, plus or minus 3 divided by 1, 4 divided by 1, 6 divided by 1, 12 divided by 1. So it was nice to you because I gave you a 1 here, otherwise there would be more. But essentially we're saying, hey, here's the possible factors. What I typically do is I take this characteristic polynomial and plug them into my function in my TI-83 or higher, and then check them by seeing if plugging in 12 gives me 0, or 6, or 4, or 3, or 1, etc. I take you through that in a different video, so I'm not going to take you through the calculator work here. Essentially, it's a guess and check process, and you can obviously use the law that helps you to know how many positives, how many negatives, etc. I'm trying to make this not a 3-hour video. So let's just say I did my due diligence. I came up with one of my zeros, one of my roots is 2. Okay. So how did I do that? I plugged in 2, I found the remainder was 0, and that remainder theorem says, hey, if the remainder is 0, then 2 is a root. So what do I have left? I'm taking this characteristic polynomial, I'm writing just the coefficients, which are 1, -7, 16, and -12. Notice that's what I've written here. This is just synthetic division. I'm dividing it by my root of 2. Remember, when I do synthetic division, the first values drop straight down. Anything that happens below the line gets multiplied. So 2 times 1 is 2. That's where this 2 comes from. Anything that happens above the line gets added, so -7 plus 5, or I'm sorry, plus 2 is -5. Then again, I multiply, so 2 times -5 is -10. Add those together, I get 6. Below the line, 2 times 6 is 12. -12 times 12 is a remainder of 0. If this isn't 0, I did something really, really wrong. So what does that tell me? That tells me that this guy factors into r minus 2. The 2 comes from here. Remember, I'm just subtracting the root. And what's left over? Well, this was r cubed, so this is 1 less than that, 1r squared minus 5r plus 6. This is now a quadratic, which is very easy to factor. So if you'll notice, I now have my fully factored form, r minus 2, r minus 2, r minus 3. The roots are then positive 2, and positive 3. Now if you'll notice, as I've indicated, I've got a double root, but good news is we already know how to handle that. So far, we've done steps 1 and 2. We've found our characteristic polynomial, we've found our roots, etc. Now that we've come up with our roots, what we need to do is write the correct format. And again, we're dealing with the fact that I've got a double root, and we already know how to deal with that. I've got a times 2 to the n. Because I have another 2, it's b times n times 2 to the n. And then this guy is a single again, so c times 3 to the n. Just as I did before, I'm not going to spend time on that. I used this initial condition to come up with my first equation. I used my second initial condition to come up with my second equation. And I used my third initial condition, that is a bad color, to come up with my third equation. So I have 3 equations. Now from here, I don't care which method you use to solve. I just need to know that you know how to solve a system of 3 equations. You're in Combinatorics, you've taken several classes where you've had to solve a system of 3 equations. I'm going to take you through how to use matrices to do that, which you probably did in linear algebra as well. So hopefully it's a skill that you're really good at. If not, feel free to solve it in what other method you like. So here, and I'm going to try to talk through it as well as I can, but again, I'm assuming you already know how to do this. What I'm going to do is I'm going to use an augmented matrix, which means I'm just using the coefficients 1, 0, 1. On the other side of the augmented matrix is the solution. That's for my first equation. My second equation gives me 2a, 2b, 3c equals 2. And my third equation, 4a, 8b, 9c equals 0. What I'm trying to get to, in case you don't recall, is I want my solution to end up looking like this. On the left side, the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. On the right side, that's going to be my 3 solutions. So that's our goal. It's always good to have your goal in mind as you go about solving a problem. So let's take a look at how I would do that. To get to my next iteration of my augmented matrix, what I'm going to do first is I'm going to focus, and again, totally personal preference here, I'm going to turn those 2 values into the zeros that I want. That's what I'm going to do first. So this guy already has the 1 that I want. Well, that's a Grease song. Start singing it in your head. 0, 1, 0, and 1. Now to get this guy to be a 0, I would have to add -2. So think about taking -2 times row 1 and adding it to row 2. So -2 times 1 is -2 plus 2 is 0. That's what I wanted. -2 times 0 is 0 plus 2 is 2. -2 times 1 is -2 plus 3 is 1. -2 times 1 is -2 plus 2 is 0. I'm going to do the same thing for row 4. How could I turn this guy, I'm sorry, row 3, which is a 4. How would I turn 4 into a 0? I would add -4. So I'm going to take -4 times row 1. -4 times 1 is -4 plus 4 is 0. -4 times 0 is 0 plus 8 is 8. -4 plus 1 is -4 plus 9 is 5. And -4 plus 1 is -4 plus 0 is -4. So I have reached my goal of getting those 2 zeros where I want them to be. Now I'm going to focus on, let's switch up colors. I'm going to focus now on, let's make sure that I have zeros where I want them in this row. I'm not going to worry about that 2 yet. I do that at the end. So I'm just going to get zeros in that second column where they're supposed to be. Lucky me, my first row already has a 0 exactly where I want it. Yay me. So I don't have to do anything to get that where I want it to be. My second row already, we're not going to worry about the 1, the 2 that needs to become a 1. We'll deal with that later. So I'm just going to rewrite this row 2 as well. Nothing's going to change. Row 3, I'm trying to turn this guy into 0. How would I turn that into a 0? Without, here's the key, without messing up my 0. So what I'm going to do is I'm going to take this guy times -4 and add it. So Negative 4 times 0 is 0, plus 0 is 0. So good. I didn't mess up my first 0. We don't want to undo things that we've already done. Negative 4 times 2 is negative 8, plus 8 is 0. Negative 4 times 1 is negative 4, plus 5 is 1. And then negative 4 times 0 is 0, plus negative 4 is negative 4. So far, so good. I bet you can guess, based on the pattern, what I want to do next. So what I want to do next is I want to make these guys 0. So do I have a 0 any of those places? No, I sure don't, but we can pretty much guarantee that this row isn't going to change because I don't need to make a 0. So I'm really just going to change row 2 and row 3. Again, my goal is to do that without messing up the zeros or the 1 that I already have in the proper place. So how am I going to do that? Well, let's look at row 1. If I'm trying to get rid of this 1 and turn it into a 0, I would have to add a negative 1. So what if I took this guy times negative 1 and added it? So negative 1 times 0 is 0, plus 1 is 1. Good, I didn't mess up my 1. Negative 1 times 0 is 0, plus 0 is 0. I didn't mess up my 0. Negative 1 times 1 is negative 1, plus 1 is 0. And negative 1 times negative 4 is positive 4, plus 1 is 5. So far, I've been very successful. Now what do I need to do? I'm trying to turn this guy into a 0. I'm going to do the same thing I did before. So how do I turn 1 into 0? I have to add, hey, negative 1 again. So 0 plus 0 is 0. 0 plus 2 is 2. Negative 1 plus 1 is 0. Positive 4 plus 0 is positive 4. Now, as you can see, I'm super close to where I want to be. I've got all the zeros where I want them. I've got mostly everything exactly where I want them. The only thing I don't have is I really need this guy to be a 1. And so this is actually the easiest one. Notice row 1 will remain the same. Row 3 will remain the same because those are already in the format that I want. And then row 2, all I'm going to do is take everything times a half. So a half times 0 is 0, a half times 2 is 1, a half times 0 is 0, and a half times 4 is 2. So what have I just done with all of my work? I have found that A equals 5, B equals 2, and C equals negative 4. So now I'm going to take this equation and I'm going to replace A with 5, B with 2, C with negative 4, and then do any simplification that I need to do, and that is my final solution. Now, I have given you a practice one of these. Feel free to go through it. I suggest that you go through it. Just know that when I go through it with you, I am not going to take the time to go through all of those matrix steps again. So we're going to try to get through it as quickly as we can. At this point, you either know matrices or you don't. You either know how to solve a system of 3 equations or you don't. So again, press pause, try the whole question. When you're ready, press play to see how you did. And let's take a look. This obviously is 4 equations, but this is why we're using a matrix, because it's just so much easier to use a matrix than it is to try to solve using another method. But again, here was my initial equation, or my initial recurrence relation, and my characteristic polynomial looked like r to the 4th minus 5r squared plus 4. Again, you can't just call this r0, r1, r2 because of the difference between the values there. So this was r4th, r squared, and r to the 0. When I factored, I came up with r squared minus 1, r squared minus 4, which then became r plus 1, r minus 1, r plus 2, r minus 2, difference of squares pattern, which means I've got 4 distinct roots. It also means I've got 1, 2, 3, 4 initial conditions, and because I have 4 initial conditions, I have a system of 4 equations with 4 variables, a, b, c, and d. Again, as promised, I am not going to take you through step by step how I came up with my values for a, b, c, and d, but I used the same process that I did in my last question, and therefore when I was done I came up with a is 1, b is 1, c is 0, d is 1, which I then used here, replaced a with 1, b with 1, c with 0, and d with 1, and came up with my final solution. So if you were able to do that, kudos to you, well done. Feel free to take a screenshot of that to check my work on all of the matrices, since I didn't take you through that step by step, but that should be your final solution. Let's take a look at a word problem that we can solve using a recursive function. So I want to climb n stairs. I can take steps 1 at a time, 2 at a time, or a combination of 1 and 2 steps, and I want to solve it recursively. So let's let a sub n represent the number of ways to climb n steps. So if I'm looking at 1 stair, obviously there's just one way to do it. I step on that stair. If there are 2 stairs, I can either go to the second stair immediately, or I can take 1 stair and 1 stair. A3, that means 3 steps. Well, I can either take 2 steps then 1, or 1 step then 2, or singles each time. You get the idea. My question is, can you find a pattern? Or that is, can you essentially explicitly define a sub n, or can you define it recursively in terms of the previous terms? So if this is my pattern, 1, 2, 3, 5, 8, is there a pattern that you can notice in those values? As you may have noticed, essentially what I'm doing to find 2 is to take 1 plus 1 to get 2. To find 3, I'm taking 1 plus 2. To find 5, I'm taking 2 plus 3. To find 8, I'm taking 3 plus 5. So really all I'm doing is using a recursive algorithm to add the 2 previous terms. My question is, does this make sense in terms of the actual problem? And hopefully we can see that it does. So if I'm dealing with however many steps, this is my last step of n. So if my last step is 1 step, okay, so here's all of my steps, this is just 1 step here, then how many steps happened before this? Well, a sub n minus 1. So however many steps it took to get to that point, plus that 1 extra step. If I'm in that same situation, but my last step is 2 steps, so I'm taking 2 total steps, how many steps happened prior to that? A sub n minus 2. So hopefully we can see that it does make sense, that I'm really just looking at 2 cases, if I end with 1 step or if I end with 2 steps. So this is my recursive relation, and again I can justify it by looking at a case-by-case basis. So how do I finish the word problem? Well, I need to solve the recurrence relation. Again, this is just a typical recurrence relation. This one's a little bit tougher. You probably noticed, although I didn't make it explicit in the last slide, that the pattern of adding the 2 terms before to get the next subsequent term is really the Fibonacci sequence. So it's the same pattern that we're looking at. I'm not going to go through all of the math with you step by step by step here, but essentially what we're looking at is exactly the same steps that we went through before. We put everything on one side, set it equal to 0. We wrote the characteristic polynomial, and then we found the roots using, in this case, the quadratic formula. And our roots in this case happen to be, complex numbers where we've got some radicals and things like that. So as I continue through all of the math, it's really just algebra. Again, really easy to make a mistake, but all it is just algebra. So I'm going to leave that up there for you to take a look at. But remember, when I get to the end, I have essentially solved for the Fibonacci sequence.